Hello everyone, welcome to the third lecture of vibrations and waves. In the previous lecture we discussed the physical pendulum and the simple harmonic oscillators without introducing any drag to the system. Today we will be discussing the situation where you have an oscillator like this spring. In this room there is air, there is drag, so the spring is oscillating, but the oscillation and vibration is decaying in time. But before we get into that, I would like to come back to the solution for the spring, but now we're going to solve it using a complex potential. So we know I'm going to start from the differential equation. I can write it as x double dot plus I could write k over m and so on, but I'm gonna focus on the equation itself. So we look at omega squared times x equals 0. You know what's omega for this system, but you can also think of other systems, and for each simple harmonic oscillator you would have a different omega. Alright, so we have omega squared times x equals 0. I guess a solution in an exponential form to be some constant c e to the power p times t. We plug this solution into the equation and we find p. So let's do that. The second derivative of x would give p squared ce times pt plus omega squared x is just ce to the power pt, so ce pt equals 0. So this part cancels out with this part, and we have p squared plus omega squared equals 0. So the solution is p equals plus or minus j omega. We have two solutions. So we can use both solutions to have the general solution of the differential equation. So we can write x equals c1 times e plus j omega t plus c2 e minus j omega t. Now, what is C1 here? C1 here, if you remember last time when we discussed complex exponentials, I asked you to look at that j as an instruction. So basically C1 is a vector which is rotating by omega t. C2 is the same, is a vector which is also rotating. So in principle I could add a phase to this rotation and still satisfy the equations. We can already go one step further, and we can assume that C1 and C2, so that the vectors have the same lengths. Now if C1 and C2 are the same, and we introduce the phases, so we can have c e to the power j omega, let me already write it as follows. So j outside omega t plus alpha is the phase, plus ce minus j omega t, and again plus alpha. This would still satisfy my equation if C1 and C2 have the same length. Alright, now this is 2c cosine omega t plus alpha Remember, we always want to go back to the physical problem. We want to go back to the real part. And this is, if you consider this as the amplitude, so you have A cosine omega t plus alpha. So as you see, there's nothing new here. It's the same solution that we had before with the cosine, but now we get to the same solution using the complex exponential. Last time I showed you the solution for the general physical pendulum, and also I asked you to do something with the hoop. I gave you only just the final solution. In the book, you have, in the third chapter, you have few good examples that I would like you to go over. But I'm just going to mention one example here, and that is the floating objects. Okay? So if you have a floating object, all right, floating objects. So we have an object. This object is floating in the water. We know the density, we know the mass, we know the cross section. Newton's second law, F equals ma. If we consider this to be as the y direction, then my double dot has to be equal to the buoyant force. And the buoyant force, I'll remind you, that would be a minus g rho a y. That is the buoyant force. Okay, so y double dot plus rho g a over m times y equals 0. Again, we're back to the same type of equation. So omega squared, or omega is square root of rho g a over m, and thus t is 2 pi square root of m over rho g a. Let's just use some of these numbers that you have in the book. If you take m, just to give you a feeling, to be 10 to the minus 2 kilograms, and a to be 2.5 times 10 to the minus 5 meters, g, let's take it 10, and rho is about 1.2 kilogram to meter cube. Now if you take these numbers, you have a very small object. This would give you, if you plug the numbers there, a period of about 1 second. You can do the same with a ship. So if you take a ship, right? This is the ship, and let's assume that this is what's in the water. Okay, this is the ship. I'm just typing the period. In this case, would be 2 pi square root of h over g. So if you know that this part, which is immersed in the water, is let's say it's a large ship, it's 10 meters deep in the water, then if you plug that there, you would have 10 over 10, about 6 seconds. So the period would be 6 seconds. And this is what you would feel actually when you're on the ship. And now you can take the other, you can solve the opposite problem. If you are on the ship, you can take the timer and calculate how much it takes for the ship to oscillate. For one oscillation, you can take 10 oscillations if you want to be more accurate, and then you divide by 10. We've done that in classical mechanics with other demonstrations. So you take 10 oscillations, you calculate the time, you divide by 10, and you have the period now. Now you can calculate how much, what is the depth that is immersed in the water. The same thing if you're going sometimes when you just step, you want to go in a boat, in a small boat, you have these oscillations. You can actually calculate the period of this oscillation. Maybe it's better to do it when you're already on, not when you're stepping in. But you can calculate these oscillations, and you can be quite accurate with these. So this is a very applied problem. But this is all so far without any drag, which we're gonna introduce now. All right, so we take a system. This is the spring. Can be any system really, because as you've noticed, the equation is the same equation over and over and over. So we have this system now. You see the spring is oscillating. We're gonna get to this later on. This is a good spring. It oscillates for a long time. This says something about the quality of the spring, which we're gonna discuss later on. But as it oscillates, the amplitude is decaying, is slowly decaying. So if I want to make a drawing of the amplitude, then it would start like a cosine, but slowly the amplitude would go down and down, right? So the amplitude, which is a function of time now, without damping it will just go. Let's do that first. So without damping, this is what you have, and with damping, it would start maybe something like this, and then now I want to be careful here. These are two different systems, and there's a reason why I say these are two different systems. Later on you'll understand why I say this. But what's important now is that with damping, is that this amplitude is decaying. If the quality of the spring, for example, is good, or if the system is good, then it takes many oscillations before the system starts damping. If the quality of the spring is not that good, so it's a low quality, it's a low number, then what you will see is something like this. So it will decay rather fast. Alright, I also want to remind you with the drag force, or the resistive forces. So we had from classical mechanics the resistive force. We wrote it in the following way as C1 times the velocity plus some constant c2 times the velocity squared. And we discussed two different situations, if it's a very viscous medium or if it's almost not viscous at all. So if the drag is very small or if the drag is very large, then one of these is dominating. We will make an assumption that we are in this domain. Okay, so we don't want to introduce the v squared in the equations. Otherwise, we will have some difficulty in solving the equations analytically. So let's get started. Let me do it there. Okay, so the decay of 3 vibrations. Okay. We take the system with the spring, mass m, constant k, and we consider now the decay, so the resistive force would be C times, I'm going to call it B now, B times V. Okay, so this would be the constant. All right, let's write the equation. It would be m x double dot F equals ma. On the other side we have the minus kx for the spring and minus b times v. Now I bring everything to the left side, so we have m x double dot. Let's bring this first, plus v, the velocity, that would be x dot, plus kx equals 0. We divide by m, so we have b over m x dot plus k over m x equals 0. Now I want to give this a name. That would be gamma, and that would be omega 0 squared. Now, there's a reason why I call this omega 0 squared. It reminds, well, without damping, we would have omega squared. That would be omega squared. So, with very small damping, we would expect that this would dominate, and then you would get a domination of this omega 0 squared, which is the frequency of oscillation in that case. But let's see. So we call this gamma and this is omega 0 squared. So now we can write x double dot plus gamma x dot plus omega 0 squared times x equals 0. This is the equation of motion. Okay, at this stage, you can say, okay, now we translated the physical problem into mathematics. Now we want to solve this equation in order to be able to predict different situations different situations for the physical problem. Now I'm going to jump into the complex domain. So instead of using x, I'm going to use z. So I'm going to replace everything with z. It's just more convenient for me to remember that whenever I'm using z, that's the complex domain, and when I use x, that's the real domain. So I'm going to use z, omega 0 squared, z equals 0. Okay, so this is the differential equation that we want to solve. I can assume a solution for this equation. So the solution would be in the form of some amplitude e to the power j times p plus pt plus alpha. Now, why do I assume this solution? I know that this solution worked previously, so I'm hoping that it might work also now. We do the same thing now as before. We substitute this solution into the equation. So we have the second derivative, and we have a first derivative here. Now let's do this here. Z double dot, we have a minus p squared. Now you see that everything would be multiplied by the exponent, and this is one of the advantages that we're using this this form of complex exponent in the solution. So I don't really need to carry on and multiply everything with the exponent here. So everything would be with a times the exponent, right? I can leave it for outside for later on. And later on we're gonna drop it completely. So the first term would give me a minus p squared times everything. The second term we have jp, right? So plus times gamma, so gamma times jp. The third term would be simply plus omega 0 squared, and this whole thing would be e to the power times e to the power j pt plus alpha equals 0. So as you see, we could just ignore this, and in the future I'm not going to even bother to write this down. So what we have here, we have a minus p squared, it's an interesting equation, plus j times gamma p plus omega 0 squared equals 0. This is the equation that I want to solve. I want to find what is that p. Now you might think that p should have relation to frequency, and you would be right? Because without the damping, for example, it would be exactly the frequency, right? You can see this immediately here. If I drop this term, then minus p squared is omega 0 squared, and that is exactly the frequency of the system. But the situation now, we have gamma here, and to solve this we have a problem. There's one equation. If I substitute p equals 0, then there would be no oscillation. I can do that. I say, well, to solve it, p equals 0, because this is imaginary here, right? Because I cannot this is the only imaginary term here. So p has to be equal to 0, but then there is no oscillation. The other possibility is that gamma equals 0, and that solves the problem. Well, not really. That actually drops the problem completely, because if gamma equals 0, there is no damping at all, and we're looking at the scenario where we do have damping. So how do we deal with this? P doesn't have to be a real number, actually. To solve this problem, you can think of P as a complex number, which means we don't have a single equation here, really, but we have two equations. So let's do that. Let's take P and we write P equals some real number n plus j times s. So P is a complex number. N and s are real. Now we substitute back. Let's see if I can somehow fit this. Right? Okay. Now we substitute P back into the equation. Well, first, let's take P squared. All right, we have a P squared there. Let's do it by steps. P squared is n squared plus 2njs plus minus s squared. All right, so let's substitute this there. Now we need to be careful with taking minus p there. So we have a minus n squared this is the dead zone. We have a minus n squared. We have a minus, we're going to write 2jns minus would be a plus s squared, that is p, plus j gamma times p, that is j gamma n, and then j gamma times js, that's a minus gamma s, plus, right, plus omega 0 squared equals 0. Let's check. I think it's fine. If you notice anything strange, please do type in the chat. I think this is correct. And now we notice we have two equations here and two unknowns, n and s. We have two equations because we have a combination of real and imaginary parts here. So let's highlight these. What is real and what is imaginary? This is imaginary. And this is imaginary. This is real. This is real. This is real. And this is real. So let's write them down. The two equations. The first equation would be minus n squared plus s squared minus gamma s plus omega 0 squared equals 0. And the second equation would be minus, I can drop the j, right? Minus 2ns plus gamma n equals 0. So far, so good. We have two equations with two unknowns. Now, if we solve these equations, you find out that s is gamma half and n squared is omega 0 squared minus gamma over 4. What happens if we don't have damping? That n squared would be simply omega 0 squared. And we go back to the problems that we seen previous lectures without decaying, without damping. All right. Now let's go back and write the equations. So we can write now go back here, z equals a e to the power if I have space here, j times, well, n, that would be square root of omega 0 squared minus gamma over 4. That is the m times t plus j times st, but s is gamma over 2 times t plus alpha, the phase. Okay, managed to fit everything here. All right. And we can also write it now in the real form, so x equals a times e to the power minus gamma over 2 times t. Now we are don't be confused. I was almost confused with this. We are in the real world now. There is no j, right? This is the decay, because we have j times j there. Okay, so this term would be there, minus gamma over 2 times t times cosine, let's write omega t plus alpha, and that omega now squared would be the omega 0 minus gamma squared over 4. All right, so this is the solution. This is what we have. This is x. This is the real solution. All right, this is the solution. This term is the decaying term, and this is the oscillating term. Without gamma, without drag, this term would be 1. And we go back to the problem where omega squared is equal to omega 0 squared. If gamma is very large, then you would expect that this whole thing would go and decay very fast. If gamma is very slow, very small, then the decay would take a much longer time. Now you might think, well, what happens here when the gamma 0 squared is smaller than, the omega 0 squared is smaller than gamma squared over 4? What happens in that case? This is what we're gonna see next. What happens when this is smaller, or when this is smaller, or when they both are exactly the same? If they're exactly the same, this omega squared would be 0. Right? Let's look into that now. Before we carry on with the different cases where the omega 0 squared minus gamma squared over 4, if that is negative or positive or equals 0, before discussing these cases, I want to move now and discuss the quality of the system that I mentioned at the beginning of the lecture. So I let this spring oscillating, and if it's with a high quality, it means that the resistive forces that are acting upon this spring are very small, and therefore the quality of the system would be high. So we can define the quality of the system with letter Q, or the quality factor. So Q of the system, that is omega 0 over gamma. As you see here, if gamma is small, Q becomes large. If gamma is large, then Q becomes small. In an ideal scenario, gamma is 0 and the Q is infinitely large. So now imagine the situation that you have a quality factor which is not too large and not too small. So the system is actually decaying. And the question is, what happens to the period as the system is decaying? Now people think that the period is getting shorter and shorter as the system is decaying, but that's not true. If this is the period, this is not what is changing when we have damping. T is uniquely determined. What is changing is the amplitude, really. The amplitude is what is changing. So if I have a pendulum and I let that pendulum oscillate and it's damping because it's a damped oscillation because there's air, there's drag, there are resistive forces. You could see that in fact the period is not really changing, but you would notice that the amplitude will become smaller and smaller with time. Now, going back to the quality factor, the question is, how many oscillations do we have to wait until we get a specific amount of damping? If I know for example, starting from here, I can write the equation omega squared equals omega, right, 0 squared. Let me write it again here. That is gamma squared over 4. Gamma squared is Q omega 0 squared divided by Q squared. So I can write this as omega squared times 1 minus 1 over 4 Q squared. If we have a system with Q equal 10, that would give an omega which is 1/8% lower than omega 0. And if Q is 2, that would give an omega which is 3.2% lower than omega. Alright, so we don't really need to have a Q factor which is terribly large in order to talk about efficient systems. Now this spring is still moving all this time. Alright, so for the amplitude, and this is a practical question that we want to ask, for the amplitude to go down by a factor of E, how long do we have to wait? We have to wait 2 over gamma seconds for the amplitude to go for a factor of E, right? If I write this down here, x goes like, right, a e to the power minus gamma over, and then you have a cosine here, gamma over 2. So for the amplitude to go down by a factor of E, this is time t. Then I'll write it down here. For A to go down by a factor of E, we need to wait for a time, say tau equals 2 over gamma. We can also ask how many oscillations it takes for the damping, and you can write then the time, that is the number of oscillations times the period. And the period of the system is almost like the period without damping, so we can, it's almost, so we can write n times t0, and that is n times 2 pi over omega 0. So if you know omega 0, you can calculate the number of oscillations required to have a certain reduction in the amplitude. Alright, I'm going to show you a demonstration here. If I go back to this point with the quality factor, here, I see the gamma down there, and if you recall what gamma is, I'm going to type it on this side. Gamma is B over M. So if I have the same shape, I have two objects with the same shape, And B is the same, it's the same constant. It has to do with the let's say with the air drag here in the room. But we have different masses, two different masses. Let's say I have two balls, one tennis ball and the other one is a light ball. What do you expect to see in terms of the damping? The larger mass would have smaller gamma. If gamma is smaller, then the quality of the system is larger. So the larger the mass is, the more oscillation the system would make before the amplitude reaches a certain amount as it decays. But if m is smaller, it would reach that amplitude, so it would decay much faster. And we're going to see this in a demonstration here. I have these two balls. Is the same length, the pendulum, so without damping you would expect them both to have the same period. But because we have damping, they would start losing from their amplitude, but also because this one is lighter, the white one here is lighter than the tennis ball, then you would expect this to damp much faster than or at least faster than the tennis ball. Let me change the angle. Well, if you can still see this, let's put this a little bit higher. And this one. Alright. This should be clear now. Alright, I'm going to move both of them and release them at the same time. They start with the same amplitude. It is the same period, more or less. Differences also in the length. It's a qualitative demonstration. But you see, this already lost most of the amplitude. This one is still running. This is still going. And that one, lighter one, almost wants to stop. Even though the mass differences between both of them is not really great. It would be a better demonstration if you use a steel ball, for example, with a styrofoam one. All right. The last thing that I want to go over now is the different scenarios of damping. So the solution that we derived is x equals a e to the power minus gamma over 2 times t cosine omega t plus alpha, where omega squared is omega 0 squared minus gamma squared over 4. Now, if we have damping or under damping, so we're looking at the case where omega 0 squared is larger than gamma squared over 4. And what we see in this equation In this case, this term would be the decaying term. It decays exponentially depending on gamma. If gamma is large, then the decay is large. If gamma is small, then it would take longer time to decay. And I can make a sketch here, for example, for the decay. So this is the exponential decay, and the system would go something like that. It's a decay in the amplitude, remember, okay, this is the amplitude, not in the period. The period is unique. Okay. What happens if now gamma 0 squared is smaller than gamma 0 squared over 4 is larger than omega 0 squared? This would be overdamping. So this is a very large damping. And in this case, we go back to our n squared, which is omega squared minus gamma squared divided by 4, which we called omega here because it was the frequency of the system. But in this case now gamma squared over 4 is larger than omega 0 squared. So we end up with n squared equals minus gamma squared over 4 minus omega 0 squared. So this is positive. I put it this way because this is positive, this is a minus sign, so n now is imaginary. So we have to go back and solve the two equations that we had. We're going to get a different solution. Alright. So in this case, n would be plus or minus j times gamma squared over 4 minus omega squared, omega 0 squared. This is n. N would be with square root of this. Well, you can define this as the whole thing as beta. So you can simply write n equals plus or minus j times beta. You see that? Yeah. So now we can look back at the exponent. We will have two possibilities, either minus gamma over 2 plus beta times t, or e to the power minus gamma over 2 plus minus beta times t. Now that is out of it's inside the dead zone here, so I'm going to remove this. I'm just going to write here, it's two solutions. You'll have either plus or minus. So the final solution for x would take the form and this is the special case when we have overdamping. So we are still with overdamping, very large damping. So x now would be a e to the power minus gamma over 2 plus beta times t plus a2 e to the power minus gamma over 2 minus beta times t. This is the solution for overdamping. It's just for completion right here that here beta is gamma squared over 4 minus omega 0 squared, square root of that, and this solution is for large damping. And the first thing that you notice, there is no cosine anymore. It's just the exponentially decaying function. There is no oscillation at all. The last possibility is that, so we looked at omega, what happens when omega 0 squared is dominating. So you can think about it in terms of the physics. If you have the spring omega 0 squared, that would be that the spring force is actually dominating over the resistive forces, and that would be the underdamping. But you have also the scenario where we just did now, where the gamma squared over 4 is larger than omega 0 squared. So the resistive forces are dominating the spring force, and therefore we have overdamping. It's a very large damping. There is no oscillations at all. And finally, there is one more scenario, and that is when these two are equal. So let's look into that. So when omega 0 squared or omega 0 is equal to gamma over 2. And it's exactly equal. This is called critical damping. Now, in this case, you would have something like this, the final solution. I would like you to verify that. Some constant A plus B times T e to the power minus gamma over 2 times T. So notice now you have two parts, unlike the overdamping, which you only have the exponentially decaying part. Here you have also this growth, the linear growth. So these are the three parts, and with this I'm concluding the lecture today. There's one more thing I would like you to watch about the three different scenarios, and you're going to see this in the video. Alright, that's all for this lecture. Until next time.